Okay, let's start with quantum mechanics. And let's start and end with quantum mechanics, of course. They can be one topic covered in a video. So we'll be talking about one interesting topic which is important for telling or knowing the difference between classical physics and quantum physics or quantum system. It's better if I had physics right now for now. Okay, so when we talk about classical physics and quantum physics, okay, so what I would like to discuss is, okay, let's suppose we have an example. Okay, we have an example that uh, there is a car. Okay, there is a, ignore my car, which is a truck. And what happens actually is it moves. It moves. Okay, when it moves, what actually happens? Why does it move? Then because of engine engine's power, right? It applies a forward force. Forward force applied. Okay, so here what's happening is when any action is done, what happened? There was a reaction in there was a reaction, but but it was only in uh, it was in but it was not instantaneous. It was not in sorry instantaneous. Okay, how it was not instantaneous was that the velocity, the reactional velocity, was less than the speed of light. Okay, which is 3 times 10 to power 10 power 8 meter per second. Um, so which is, I think, if I remember, if my memory is correct, 299 uh 7, I forgot, sorry, but doesn't matter. This is our average value. So hmm. So here this is something known as locality. Okay, locality is restricted. Okay, so when I talk about restricted, we will we will know what this word is, why we use this word here, and why it's so important. Restricted. Okay, now important. Okay, so this to the region or space. Okay, meaning that this is our space or region, whatever you want to call. In this space, if something, let's suppose a ball moves, a ball is kicked. Okay, it moves in reaction. So the things are happening within the region, within within the region. Okay, within the region. But even same goes for relativity. Relativity, because relativity comes in classical physics, so this is also part of it. That if we have two planets and A, B, there's a twin which goes to planet X from P. So when moving, both both compare, and compare is a very important word here. Compare, because if there is comparison, then there is locality. Okay, so meaning there he will the person, the A, he will have his own clock, his own clock on his wrist, and that clock will be slowed, as we know from general relativity, will be slowed. Okay, why would it be slowed? It would be that if it's because of its speed equal or less than or equal to c, it's near it, I'm trying to say. And this formula and is applied in, it's been a while I wrote this formula. Gamma, wait, this gamma doesn't fit here. Gamma is equals to 1 over root of 1 minus v over c squared. And I messed up, I knew it. This is changing time. Depends on how many years we're talking about. How many years? But mostly when we do comparison, when we have like normally we use 1, because we mostly want to know the 1 year difference. So comparing sorry comparing to earth time. Now look at this again, comparing is here, so locality. And so first point of locality is that it's restricted in a region. Second point of locality is comparison. Two of these, compared, both are compared. So now uh, what would be the opposite of locality? Right, correct, it is non-locality. Now most of you must have understood non-locality is the opposite of locality. Opposite of locality. Now how is it opposite? Okay, so if we talk about CPS, oh by the way, I didn't say that, but CP is localities from classical physics. But now since we have entered the domain of like non-locality, we have to go to quantum mechanics. We have to enter the domain of quantum mechanics. Now, how does quantum mechanics explain? How does QP explain non-locality? Right? Locality. Okay, so Now, here we have a particle. Okay, here we have a particle, and it's in superposition, or it would be better to so we would, if we use entanglement, is better to use because it doesn't it gives more understanding of non-locality in and it is easier to explain to others that how non-localities works actually while keeping the interest. So p1 particle 1, p2 particle 2. So now, since we also know that this phenomena which is now possible, entanglement, quantum entanglement, what does it do is uh, two particles p1 and p2, they somehow, when I say somehow, I don't have an explanation of, because this is the weird nature of quantum mechanics, that we have two particles, from nowhere they will be an in a state that they will share the properties. If I say share properties, I would mean that their properties are in they have a connection. Their properties have connection, and this connection has a very this connection has a name, and this name is, let me name it. Yes, a name, very famous name, which was given by Albert Einstein. Spooky action at a distance. Spooky action at a distance. At a distance. Because what we observe here is, and he wasn't draw like he was not like he couldn't believe, because what this spooky action at a distance is saying is information is faster than speed of light. Now that's a huge issue for Einstein, because his whole whatever he did in his life was all about speed of light. His whole career was about speed of light, the theory of relativity, special relativity. All of it was based on this single concept, speed of light. So, as because keeping classical physics touched, that we will keep in touch with classical physics, that in classical physics information was slower than speed of light. How? There's a ball kicked, there's a reaction, right? It doesn't happen instantly. There's just some gap limit. Even though it's less time, it's in milliseconds, but there is some time which is in between. Now, then, um, let's suppose what else? A rod moving. Someone moves it. There's a reaction, but in of course the reaction is not within the time limit. Wait, let me see. Where did I write? Sorry, wait a minute. Let me write it properly. The the change in time is actually in milliseconds. Okay, so that's why we don't notice that much of a difference. Okay, so yeah, but still, again, milliseconds doesn't confirm instantaneous. it's still below speed of light. So instantaneous, the speed of light, the boundary of speed of light is not like crossed or reached. Even reaching it is not possible according to classical physics. But then here, the shocker is that information is traveling faster than speed of light. How? This particle's property, properties, and this particle's properties. Property one, properties two. There's a huge connection. What happens? You know about this? You know about this particle? You know about this particle's property. If you get this particle's property, you know this particle's property. So there's a um, again, I don't have any words for what how this connection is made, but this is proven that there is a connection through Bell's theorem, Bell's test. Okay, in which particles are, of course, I think photons were the ones which were captured, which were shot, and there was locality observed. Sorry, not locality. Mean quantum entanglement was observed. Quantum entanglement entanglement was observed in Bell's test. Sorry, I think I got off topic a little. But then again, non-locality again has the first of all, what was it? It's opposite of locality. Second of all, information is faster than speed of light. The main information is faster than speed of light. I mean the amount of time it took for us to know the information was instantaneous, speed of light. Or it wouldn't be. Should we say speed of light? Well, fine. So uh, the point here is when classical physics is fixed, has a range, has a boundary, has restrictions, but quantum mechanics, even if you put restrictions, it will just go through them. It doesn't matter for quantum mechanics, like because uh, I think I just made a weird like something in my mind. Let's suppose uh, yeah, because it's funny, so let's just do it. Let's suppose this is restriction, okay, and this is classical physics. It's going towards restriction. Let's suppose restriction is a wall. uh, it's called wall of below restriction. So classical physics is going towards restrictions. Okay, now the point of contact point. Okay, what happened on the contact point? Classical physics was bounced off, but here comes quantum mechanics majestically with its weird behavior phenomena and many more things. Here it comes in. We observe quantum mechanics actually phasing through and reaching here. So this is the difference between quantum mechanics and uh, classical physics. It doesn't have any restrictions, boundaries. It's a weird phenomena. Everything has its nature, but the nature doesn't tell us what it is or how it works. we can just write mathematical forms of for CP and QP. But then when we talk about um, again locality and non-locality, if non-locality refers to not having any restrictions, and again uh, talking about not having restrictions, this distance over here uh, can be large, long distance, okay, which is over here, while over here we were stuck with certain boundaries. Restriction mean region, we were stuck in a region. This region, how far could it go? Only this much, right? But when we talk about long non-locality, long distance, even billions of years, doesn't matter, we get the instantaneous result. And of course quantum entanglement is the best example of non-locality. And in locality, of course I would for me I would prefer relativity as the best example for locality, because again it comparison, the word comparison is actually the main thing here, because it comparison is being made, but in quantum mechanics there's no comparison. The moment you do something, changes happen, system is destroyed. This is QP, okay, running smoothly, but CP plus QP equals to CP. What I mean by is observation. I may be wrong, but this is what I think. This is classical physics observing quantum physics, which 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 results in classical physics. Because what happened is, it's me. I'm there's so sorry. There's a person. That's supposed me. I suddenly look at an electron. I don't know what that electron was doing. It was of course in superposition state, because that's what quantum mechanics is. Nothing is observed. It's in superposition state. But the moment I observed it, it was one. It was at a certain point. It, like if this is superposition of electron, so what happened? It broke into one of the probabilistic state. Again, the word probability is very important. And okay, what more? Like in non-locality, the word probability is used a lot, because quantum mechanics does depend on non-locality, probability. But in quantum mechanics, classical physics, we get definite values. We don't have probabilities. We don't say that there's a probability of this, there's a this much probability of this happening or not happening. But when classical physics is all about exact values or exact predictions, we don't have to worry about either we will have probabilities or not. But quantum mechanics, yes, again probability is very important. Probability density probability sorry probability, okay, which is here, okay. Thank you.